Alright guys, so this is our first video on inverses, and in this video we are going to talk about inverses graphically. In general, we're going to say an inverse reverses or switches the x or the input and the y or the output. So if we're looking at a point defined by an ordered pair, let's say we've got the point 2, 6, the inverse of this point is going to be the ordered pair that switches the x and the y value. So that's going to be the ordered pair 6, 2. And in general, what we can say is that these 2 points are actually inverses of each other. They switch each other's x and y values. So they share an inverse relationship. And in general, what we're going to see is this inverse relationship actually extend to a function and its inverse. Right? So in general, what we can say is that a function's inverse is going to take all of the x and y values from the ordered pairs that make up a function and switch them to get the graph of that inverse, right? So right here, if we have a function, let's say f of x, right? We would say that the inverse of f of x would be written f to the negative 1 of x, and we would say that that is f inverse of x. And we would say that the inverse of f is going to be the function or relation that switches the members of a function f's domain with the corresponding members of its range, and that is the inverse of f. So again, right here, if we are taking all of the ordered pairs from the graph of f of x and switching the x and y values to get the graph of f inverse, then of course what that's going to mean is switching the domain and the range. In general, we want to say that the inverse reverses the actions of the corresponding function. And if we think about the function as taking an input and giving an output, right, and the inverse basically switching that input and output, really what the inverse is doing is undoing what the function did to its input to give that output, right? So basically right here, a function takes an input, does some mathematical process to it to give the output, right? And the inverse is going to be something that basically takes that output and gives back the input, basically reversing that process, right? And we're going to see that in the relationship between our first function and its inverse right here. So first we have the linear function f of x, and we're saying f of x is going to be 2x minus 3. And f inverse of x, in this case, is going to be x plus 3 divided by 2, right? Now, if these guys are actually inverses, then f inverse should take an output of f and give the corresponding input, right? So let's take, for example, negative 9. So if we take negative 9 as an input of the inverse, then right here we would say f inverse of negative 9 would be right here negative 9 plus 3 divided by 2, which is going to be negative 6 divided by 2, or negative 3. So what we can say then is that, of course, that inverse relationship works for the ordered pair negative 3, negative 9. When we plug negative 9 into f inverse, we get back negative 3. But how do we know it's going to work for every single output, right? So we could go ahead and plug in all the y values as x values and see if we get their corresponding x values. But that's going to be a long process, right? So what we want to do is be smart about it and think about what f is doing and what f inverse is doing. So f as a function takes an input and first multiplies it by 2 and then subtracts 3, right? F inverse takes its input and first adds 3, which undoes the subtraction of 3, which is the last thing that f did. The next thing f inverse does is divide by 2, which undoes the first thing that f did with the multiplication of 2. So really what we're seeing is the process of f inverse undoing the process of f. And similarly right here, if we start with f inverse, it's going to be the function that adds 3 and then divides by 2. F basically first multiplies by 2, undoing the last thing that f inverse did, the division of 2, and then subtracts 3, which undoes the first thing that f inverse does, the addition of 3. So really, again, what we're seeing is the inverse relationship between these two functions. Now, when we look at linear functions in general, what we're going to say is the inverse of a linear function is always a linear function. So right here, we've got one ordered pair, and we know that we need two ordered pairs to define a line. So all we have to do is get one more ordered pair for our inverse to define that line that is going to give us the graph of the inverse. Right here, if we plug in the x value of 1, we should get back the y value of 2 for the inverse. So right here, we can say f inverse of 1 is going to be 1 plus 3 divided by 2, which is 4 divided by 2, which gives us 2. And so right here, we are going to have the ordered pair 1, 2, which is, of course, the inverted ordered pair of 2, 1 for f. And right here, we can graph these 2 points. So we've got -9, -3, that point right there. And we've got 1, 2, which is that point right there. And I'm going to cheat a little bit and use the slope of f inverse, which you could get if you sort of converted to slope-intercept form. And right here, we are going to get the line that looks like this as the inverse. And in general, what we're going to say is that what we're seeing here is a reflection across the line y equals f between inverse functions, or inverse relations. Okay? So right here, every point on the function f is reflected across the line y equals x to give us a point on the function f inverse. Right? Now we can prove this, and I had a proof set up down here, but it took a little long, and of course we want to keep these videos relatively short, so I kept it out. We may do something to prove this. I may give you guys a little extra credit if you can prove that an inverted point is a reflection across the line x equals y, right? So if we had a point A, B, the point that is the inverse of AB, which would be, of course, BA, is going to be a reflection across the line. You may get some extra credit there. But in general, we're going to put that aside for now. And what I want you guys to do is to go ahead and try to graph some inverses on your own. So right here, we've got a green line, right, which is going to be the function y equals -3/4 x plus 2. And what I want you guys to do is to get the graph the inverse of this line. So, of course, we know that the inverse of a linear function is going to be a linear function. So really all you need is 2 points from your green line, 2 ordered pairs to invert. That will give you 2 ordered pairs that you can graph the inverse through. 2 points define a line, and 3 points define a parabola. So right here, when you're drawing the inverse of your parabola, you want to choose 3 points. Strategically, we can choose the vertex, and then right here, a point on either arm maybe to invert. And then what we want to do is graph the inverse of this parabola, which is, of course, y equals x squared. And basically right here, what we should be seeing with the inverse is behavior that's happening along the y-axis for y equals x squared. Specifically, that symmetry to the y-axis now happening along the x-axis, right? So switching x and y values means that behavior along the y-axis should then happen along the x-axis. For the inverse. So right here, we're going to stop the video, and I want you guys to pause and give these a shot on your own. So we're stopping the video here. All right, guys. So for our linear function, I chose the ordered pairs -8, 8, and 8, -4, and inverted those guys to get the ordered pairs -4, 8, and 8, -8. And I drew my red line through those ordered pairs to give me the graph of the inverse. And in general, right here, of course, we know that if these guys are inverses, we should see them as reflections across that line y equals x. And so right here, when I draw in y equals x, the line where every x value equals the y value, they do in fact look like reflections across that line. For the parabola, I chose, of course, the vertex, and I chose negative 3, 9, and 3, 9 as the points that I would invert. And that gave me 9, 3, 0, 0 as the inverse of the vertex, and 9, negative 3. And then I, of course, graphed the behavior I was seeing along the y-axis for the graph of my y equals x squared along the x-axis. And that gave me this sideways parabola along the x-axis right here. Now, in general, what we can say is that clearly the inverse for our parabola is not a function, since for the input of 9, we're seeing two outputs. We're seeing a positive 3 and a negative 3. The graph of our linear function right here is the graph, or the graph of the inverse of our linear function right here is a function, but we're not seeing that same relationship for the inverse of our parabola. And that leads us to the conclusion that a function's inverse may not always be a function. Right? We know a function is a relation for which every input has only one output. In general, we say that the vertical line test is a way for us to visualize this on the xy axis. So if I take a vertical line right here and pass it over the graph of my function, what I should see is that vertical line crossing the function only once. And what that simplifies is that one input is only giving one output, right? Now right here, for the graph of the inverse, we are clearly not seeing that same relationship. For the graph of the inverse, we're seeing our vertical line crossing the inverse of our parabola more than once, right? Right here we're seeing basically the input of 9 giving us outputs here and here, which means that the graph of our inverse is not a function. One way we can tell if the graph of our inverse is going to be a function is with the horizontal line test. And the horizontal line test basically says that if we can draw a horizontal line across our function that crosses our function more than once, when we invert all those ordered pairs, we are going to get a vertical line crossing the inverse more than once, right? And this should be pretty logical, right? Right here, we're seeing two ordered pairs where y value is paired with more than one x value. So if we switch the x and y values, we are going to see two ordered pairs where the x value is paired with more than one y value, right? In general, of course, if we go back to our linear function right here, we can see that the linear function does pass the horizontal line tests right here. That means that the inverse of this linear function should also be a function. Right here, if we go down, if a function passes the horizontal line test, we say that function is one-to-one. Basically what we're saying then is that not only is every x value paired with only one y value, such that it is a function, we're also seeing every y value paired with only one x value, right? So x values are paired with only one y value, and y values are paired with only one x value, right? And that, of course, is going to mean that when we switch those x and y values, we're seeing the inputs paired with only one outputs for those inverses. That is the definition of a one-to-one function. You guys have probably seen this before in Algebra 2. We are going to stop our video here, which gives us almost 14 minutes for the second video. And the second video should be, or the last and third and final video should be pretty short. We're stopping our video here, and we'll see you guys on the next.